All right, good morning, everyone. We'll begin lecture in 1 minute. Okay, so today is lecture number 4 of the semester, Sorting Algorithms, Part 2. Last time we discussed sorting algorithms, and if you want to write in the chat, which sorting algorithms did we learn so far? Okay, again, if you could write in the chat. Okay, we did not learn radix sort yet. We did talk about merge sort. Which other sorts? Bubble sort, BOGO sort, right? Selection, good, shell sort, insertion sort with binary search as a variation. Good. That might have been it. That might have been it. Okay, good. So today we're going to continue our conversation. Remember, that's right. We had the cocktail shaker sort, correct? Okay, so we're going to continue our discussion. Keep in mind that sorting is important, A, because sorting is an important problem, and B, many of the things we are going to learn about sorting can then be applied to other things, whether it's the design techniques that are being used, whether it is the analytical mathematics that we can use to analyze it. The sorting algorithms themselves may give us ideas of how to approach other problems. So this is, we also have the Stooge sort. Remember that? Stooge sort, where you do 2/3, you sort 2/3 of the array and the other 2/3 and the same 2/3 again, right? So that was another one. Okay, so it wasn't yesterday. Should I fix that? So part 1 was last lecture. Okay. Okay, so these are some of the other sorts we're going to hopefully cover today. Going to start with quicksort. So you may have seen quicksort in data structures, maybe not. What is quicksort? By the way, quicksort was not named after Quick, not like the shell sort that was named after Professor Shell. This was not named after Professor Quick. All right, how does quicksort work? Well, you identify an element. How you identify that element, we'll talk about that in a moment. And what you do is you take anything that's less than the element and you put it on the left side of the element. And you take anything that is bigger than the element and you put it on the right side of the element. Okay, so now you have all the small ones on one side and all the big ones on the other. And we do that recursively. Okay, it can also be done without recursion, but it's usually done recursively, right? We take the small elements on the left and we find something somewhere in the middle of them. And then we take all the ones that are smaller than that, we put that on that left, and we put all the things that are bigger than that on the right. And we repeat that process. And if we do that enough times, the array will be sorted. So if you look at this bullet over here, it says, how do we choose that pivot? How do we choose that element where we put everything less than it on one side and everything bigger than that on the right side? So there are a lot of ways of doing it. And depending on which code you get for your assignments, in some cases, it'll say just use the first element or just use the last element, or there's something called median of 3. Median of 3 means pick 3 elements, let's say the first, the middle, and the last. Take the middle one of those and use that. Why is this a good strategy? Sounds like a lot of work. What's the advantage of that? Someone tell us why. Either write it in the chat or better yet, speak out. Why is that a good idea? Because we want something that's going to be an approximate median, approximate middle. So if we just take the thing that's in the first position or the thing that's in the last position, or just grab something, who knows what it's going to be. But if you take 3 elements and you take the middle of those, it will be a better approximation of the real median. Okay, another approach, which turns out to work very well, and it's a classic example of a randomized algorithm, is just to pick one at random from the whole set. Again, the same idea, figuring if you pick something at random, it will be a reasonable approximation of the median. Okay, so that turns out to be pretty good. Now I have a note here, 2 notes about a comparison to merge sort. Okay, number 1, right? In merge sort, I have to take my 2 parts of the array and merge them together. Sometimes people compare it to a zipper, although I disagree with that analogy, right? Because in a zipper, everything is nice and interleaved. In merge sort, it doesn't always work like that. You could get a lot of things from one list and then a lot of things from the other list, right? Number two, in quicksort, there's no work at the end, right? All the small ones are already on the right, all the large ones are on the left. You don't need to piece it back together. All right, another thing about merge sort is out of place. It requires auxiliary storage, right? You have to merge the data into another list, right? In quicksort, everything is in the array itself. That's good, right? It does not require extra storage, right? There is a drawback to quicksort in that the way it's usually implemented, it's not stable. Can anyone tell us, either in the chat or speaking up, what does stable mean? If a sort is stable, what does that mean? It doesn't mean it's with the horses. What does it mean to be a stable sort? Remember, we had that right at the beginning of last lecture, right? A list of terminology. So a sort that introduces inversions that were not already there is not stable. Who remembers which sort we did that was not stable? At least one. So selection sort that we did is not a stable sort. Okay, here is an illustration of quicksort. We have our data here, okay? Somehow we decided, we just, let's say, arbitrarily picked the last thing, right? That's going to be our pivot. So we say, get me everything that's less than or equal to 3 on the left side, everything that's greater than or equal to 3 on the right side, okay? Probably wouldn't do it like that. I'd probably do greater than on one side and less than or equal to on the other side, but okay. And then we pick another pivot. So again, we're using the same convention. Pick the last element as the pivot. Anything that's less than or equal to 1 is going to go on the left. Anything that's greater than or equal to 1 is going to go on the right. Same thing over here. We pick 6 as our pivot. Anything that's less than 6 on the left. Anything that's bigger than 6 on the right. And so on and so forth. You keep doing that until you have one element left. At one element, it's obviously sorted. And so we stop. Right? So that is a quicksort. Now, here is the code, or a code for quicksort from Geeks for Geeks. Can someone tell me which strategy is it using to find the pivot? So we had several different strategies already for how to pick a pivot. Which strategy is it using? It's not using, it is a divide and conquer approach to the algorithm, but how is it choosing the pivot? No, it's not using medium 3. Medium 3 is a good strategy. It's taking the last one. So Cheng is correct. It's taking the last one, right? Take a look at this line over here, right? It's taking the last line, right? So we go from low to high, take the one from the highest position, taking the last one. Again, it's not the only way to do it. Median of 3 is better. Randomized is probably even better than that. Okay, so we're going to do some analysis. Now, as we've said before, you can do best case analysis, worst case analysis, average case analysis. We're going to start with the worst case. So in the worst case, all right, all the data is going to be on one side or the other. Okay, so it becomes like bubble sort. Why is it like bubble sort? Because you have n-1 operations to actually do the pivot, right? And then you have to process the same thing for the remaining elements. Okay, you have to process the same thing for the remaining elements, right? So all n-1 elements are on one side. So now you're going to call the same algorithm on those remaining n-1 elements. So the solution to this kind of equation is n squared, okay? So in the worst case, it's n squared. Where have we seen that before? We had that in bubble sort, selection sort, insertion sort. All of those took n squared. The analysis is very similar. Okay, let's go to the best case. In the best case, half of the data will be on the left and half of the data will be on the right. Where have we seen a recurrence like this before? This one here.
Binary search.
So it's similar to binary search. In binary search, we had T of n divided by 2 plus 1. But this doesn't say that, right? Where have we seen one more similar to this?
Merge sort.
Merge sort, right? Because we had two subarrays, each half the size. And we said worst case for the merge itself is n-1. So that's where this came from. And we showed that the solution to this, you can either do it directly or using the master theorem, is T of n equals n order of n log n, right? By the way, I will be posting old exams. Okay, so we do have a in-person final at the end of the semester, that Thursday, August 11th. And so I will be posting some of my old exams. Some have solutions, some don't have solutions, and you can get a feel for it. Just keep in mind that it is a combined final. So there'll be material from, all different parts of the semester on. Okay, then we have an average case. So just like, how do you find the average? Let's say I want to find the average of the class on an exam. How do you find the average score? What do you do?
Do the sum, then divide by the number.
All right, so you add up all the scores, you divide by the number of students, and you have an average. So we need to do something like that over here as well. We say, where is that pivot? Pivot could be in the first position, it could be in the last position, it could be in any position. So we calculate the work in all those cases. So this is the work for the left side of the pivot. This is the work for the right side of the pivot. And this is the work to divide it into two parts. All right. So we average that. That's what the 1 over n is doing. It's dividing it by the n cases. And this takes the sum over all possible positions of the k. All right. Today, we are not going to solve this, because it's going to take too long. It could take us like a half hour to solve it. It involves a lot of math. We will come back to it in the lecture on trees. You might say, well, what does this have to do with trees? And I'm going to explain to you what it has to do with trees. But for now, if I move my chat box out of the way and I move my video box, you can see at least what the answer is, right? So the answer is n log n. All right, so what do we get from that? What we get from that is, in the worst case, quicksort is n squared. In the best case, it's n log n. And in the worst case, in the average case, it's also n log n. All right, so that's pretty good. Why is quicksort called quicksort if it's not named after Mr. Quick?
It's quick.
It's quick, okay. Is it always quick? When is it quick?
Most of the time.
On the average, okay, and the best case. But in the average is quick. In the worst case, it's not so quick, right? In the worst case, merge sort is better. So why not use merge sort, which is an n log n sort? And we're going to learn another sort called heap sort, which is also n log n in the worst case. So why is quicksort preferred? By the way, in the C programming language, if I just call sort, and I don't, I call the built-in sort, it will use quicksort. Okay, in Python, it doesn't use quicksort. If you just call the native sort, it will use something more like a TIM sort, which is like a hybrid of insertion sort and merge sort. But why use quicksort? Why not merge or heap that are worst case n log n? So one answer is the space. Merge sort requires auxiliary space. Number two is that the constant is higher. In other words, in the quicksort, yes, the worst case is bad, but the average case is pretty fast. Okay, So we're now going to talk about another sort, and this sort you might not even find in a list of sorts. It's not really a traditional sort, but it works, and it's nice because people know about it. I assume everyone here has taken data structures. Has everyone learned about binary search trees? I hope, right? So we're going to use a binary search tree to sort. Okay, so how does that work? Okay, so the first thing you do is you build a binary search tree. Okay, so I'm not going to get into all the details of that, but basically you put an element in the root, and then if you get something that's smaller than it, you put it on the left. If it's bigger, you put it on the right. And that's how you build a binary search tree. You keep on doing that until you get all the elements in there. Now, how do we get the elements of a binary search tree in order? Should have learned that in data structures, right? If I want to, get the elements out in order, what do I do? Anybody? Well, even if you don't remember, it's actually right on the slide, but you should remember because this is an important thing from data structures.
Aren't there like various methods?
So you use what's called an in-order traversal. In-order traversal. Okay, traversal means to go through all the elements in a list or some other data structure, right? So we use an in-order traversal. What does in-order do? Well, first of all, we do an in-order on the left subtree, the left child and its elements. We output the root elements, and then we recursively call the in order of the right-hand side, and we get a sorted list. Okay, so again, how do we sort using a binary search tree? I'm not recommending that you do this. You build a binary search tree, you call an in-order traversal, and now you have the elements that you started with in order. Okay, so here is a binary search tree. Okay, what's the basic property of binary search tree? Can someone tell me by looking at it, what is the basic property here? If you wanted to describe to someone, a computer science student who gets stuff, but hasn't taken data structures, hasn't taken discrete structures yet. So how would you explain to them a binary search tree?
The left node is always smaller than the parent, and the
Okay,
right
good. So the left node should be either less than or maybe less than or equals, depending on whether you could have duplicates, right? Okay, and if it's greater than, it needs to be on the right. Okay, so keep in mind that the binary search tree isn't always balanced because no one's controlling, are you going to get more, bigger ones or smaller ones, right? There's a concept, and we'll talk about that, not today, is a balanced binary search tree where you can sort of ensure that it remains balanced. All right, so let's talk about this binary search tree sorts, all right? So we need to build the tree, okay? Building the tree takes n log n an average in the best case, but its worst case is O of n squared. Why? Why is the worst case n log n squared? When does that happen to build a binary search tree? So if the elements are all pretty large or all pretty small, they're gonna, they're all gonna stack, and you're gonna get what they call like a snake-like formation. It's all gonna go off to one side or the other side. So building it, the first operation is going to take 0. The second operation is going to take 1. The third operation is going to take 2. And you're going to get 1 plus 2 plus 3 plus 4 up to n minus 1 adds up to n squared. So building a binary search tree is good on the best and average, not so good in the worst case. Then we have an in-order traversal. Okay, so the good news is the in-order traversal is O of n time, right? Each node gets visited once. Pre-order traversal, post-order traversal, in-order, reverse order, all n linear time algorithms. Okay, so notice that the time here is actually spent on building the binary search tree, not on traversal. And here's why I like to mention the binary search tree, because it's very similar to quicksorts, right? Let's go back here. It's like a pivot. This is your pivot, and everything else goes to the left. Everything else, the smaller stuff goes, the bigger stuff goes to the right. And then we have another pivot. Whatever's smaller than the pivot goes to the left. Whatever is bigger than it goes to the right. So binary search tree sort is very similar to quicksort. And when we do our analysis, we'll see that the analysis for quicksort, the detailed analysis is similar to that. Okay, so that was our first sort of today. Second sort. We had quicksort and binary search tree sort. Move on to our next sort today. It's called a heap sort. All right. We briefly talked about a heap in our lecture on data structures. And what is the basic idea of a heap? Again, how would you describe a heap to someone who knows computers, a little bit of computer science? They took a programming course, but they don't really, know data structures yet. Okay, so yeah, go ahead.
A heap could be like, could be categorized as like a min heap and a max heap.
Okay, so first of all, it's a tree shape, right? You generally have nodes with binary, usually it's binary, 2 children each. You should notice 2 children unless it's at the bottom.
Can't you also be like an
it could be
array?
a min heap. Yeah, so it's you're right. It's conceptually we think of it as a tree, but you're right. It's usually stored as an array. Okay, so the way it's designed, because it's balanced, it's perfectly balanced, it will fit nicely into an array. And generally it has either a min heap or a max heap property, which means that the smallest one will be on the top, and then both of its children will be larger, right? Each node will have 2 larger children. If it's a max heap, it's the other way around. Largest one is on the top. Both of its children will be smaller. So in that sense, it's very different than the binary search tree. It'll always be balanced, meaning if you look at each row will be filled in except possibly the last elements, but it's always just filled in left to right. So how do we do a heap sort? The idea is as follows. We build a heap. Once we have a heap, we just keep getting the min. Let's say it's a min heap. We just take the min out, and we take the next min out, and the next min out. So you're gonna get all those mins in sorted order. So how long does it take? We have analysis here. Here's our analysis, okay? So our analysis, you build a heap, it takes order of n time, and then we do the heap sort. So the way the heap sort, again, you get the smallest thing. How long does it take to get the smallest thing out of a min heap? If it's a min heap, where is the smallest?
It's at the root of the tree.
It's at the root, correct. Now, once I take it out, what do I need to do after that? I can't just take it out. I need to do something else.
We delete that.
Well, you take it out, right? So you delete in the process, but what else do you need to do?
Move it to the bottom.
You need to, what you need to
replace
do
it.
is you need to heapify. You need to restore the properties. So you're going to have to look at one of the 2 children and say one of those is going to become the new min, right? And you're going to promote one of its children, right? You got to move everything up, and that's going to create an empty slot somewhere on the bottom right-hand corner of the heap, right? So that process called heapify or restoring the heap takes log of n time. Now, if we do this n times, right, because we have n mins, right, smallest and then the next smallest, right? So we get a total of n log n. So again, we need to build a heap that takes n. We need to remove the smallest, that's fast, but then we need to heapify, right, restore the property. We do that n times, we get n log n, and that's best, average, and worst. Okay, so if you look over here, we have the code, right? Basically what the code is doing is, sorry. If you look at the code here, basically we're finding the position of the 2 children. We're finding out, by the way, depending on which code you look at, some use a max heap and some use a min heap. So this approach uses the a max heap approach. So it's basically saying which of the 2 children are larger, and it uses that, and then it moves that one up. All right, so that's a basic approach. And here you see that process going on, right? So basically we're deleting the largest, we're placing it in the array at the end, but notice there's no arrow there. Can someone tell me why there's no arrow? Everything else has an arrow on it, or at least the line sign. I'm really narrow, it should be an arrow.
It's because it's not part of the tree anymore.
It's no longer part of the tree, it's no longer part of the heap. It's just at the end, right, of the end of the array. Okay, so notice what happened. After we got rid of the 16, we promote the 14 because it's the larger of the 2 children. And here, after we get rid of the 14, we promote the larger, right, the 10. and so on and so forth. And you'll notice in this last picture at the end, right? You see all the elements that were there that we put outside of the tree are in a good position. Okay, so these are the sorts we've done so far, right? We had the BOGO sort, which was that random, that weird sort. We had bubble sort, the cocktail shaker sort, where you do a bubble sort basically from left to right and then right to left. We had selection sort, where we found the smallest element and put it at the top, and the next smallest put at the top, and so on. We had insertion sort, where we always take the next element, find the right place to put it. Binary insertion sort, or we use a binary search to find it. The shell sort, which was like an insertion sort with different gaps. Stooge sort, where we do 2/3, sort 2/3, and the other 2/3, and the original 2/3. Merge sort, where you sort two halves and you merge them. Quick sort, where you get the small ones on the left, big ones on the right. Binary search tree, you build a binary search tree, and then you do in-order traversal, and finally the heap sort. Okay, these are all comparison-based sorts. Right, maybe I should fix that just to be, this time I introduced another lecture in between. So let's just say lectures, say 3 and 4. See this. There, yeah, okay. All right. All right. So this is called the decision tree model for comparison-based sorts. And what we're going to do now is we're going to show that any sort that uses comparisons is going to take at least a certain amount of work, right? What is a comparison-based sort? It means that you look at a pair of elements, you compare them, and you decide, what to do if one of them is smaller, and you decide what to do if the other is smaller. So take a look at this picture here. This is an example of comparison-based sort, right? You have two values, V1 and V2. You compare them. If V1 is less than V2, you do this. And if V1 is greater than V2, you do that. Now, we're ignoring what happens if there could be equality. Okay, if they can be equal, then you just change one of these to less than or equal and the other one to greater, right? Now, what do you do now? Well, you pick two other elements and you compare them, and depending on what the result is, you can do something on the left or you do something on the right. So this is a comparison-based sort. Now, I have a question for you, which is, how many different leaves are there? The leaves are the outcomes. The leaves are the things on the bottom of the tree. How many different possibilities are there? So let me ask the question like this. If I have 3 elements in my array, how many different orderings of 3 elements can there be? The fancy word we use in math is permutations. How many permutations of 3 elements can there be?
3 factorial.
3 factorial, correct. Okay, so what is 3 factorial here? Or in general, 3 factorial? Right, 3 times 2 times 1 equals?
6.
6. Okay, so what does that mean? It means our comparison-based tree needs to have at least n factorial leaves. Why? Because there are n factorial possibilities. So we have to cover every single possibility because we don't know, we can't say which permutation is going to happen, which is not. So they all need to be there. Now they could actually be there more than once. Why? It doesn't mean you can have the same permutation twice. It means that you might arrive at what to do in that case in more than one way, depending on which order you ask the questions. So it is possible that the same permutation will appear in more than one leaf, but every permutation needs to be there. Okay, so what this slide says is, okay, let's say there are at least n factorial leaves. What is the height? So it turns out, this is the key line here, turns out that the height of a binary search tree, or any tree for that matter, right, with, that's a binary, is at least the log of the number of leaves. Okay, that's what this says. The height of the tree is at least the log of the number of leaves. Now, how many leaves did we say we had? What did we just say? What's the minimum number of leaves? What?
N factorial.
n factorial. So that means the height of this thing is going to be at least the log of n factorial. Now, what is the log of n factorial? That sounds, ooh. The answer is, remember a rule of logs. What is the log of a times b? Anyone know? I'll write it in the chat here, right? So if I take the log of ab, what is that equal to?
Is it log A times log B?
Close.
It's log A plus log B.
Like that. Okay. So what we're doing here is we're saying, okay, what is n factorial? It's 1 times 2 times 3 times 4 times 5, right? So what is the log of that? It's going to be log. This is not a good way to write it. Hold on, this is not a good way to write it. Let's write it the right way. So this is equal to log of n plus log of n minus 1 plus log of n minus 2 plus log. That's better. Okay, so that's equal to order of n log n. All right, so what does that mean? It means that the height of this decision tree is going to be at least n log n. Okay, so now you begin to understand why these sorting algorithms have to be at least n log n, because the amount of work in the average case and the worst case has to be at least n log n. What does that mean? What does that tell us? It tells us that no comparison-based sorting algorithm will be better than n log n in the average and worst cases. I'm going to repeat that. It's very important. No comparison-based sorting algorithm is going to be less than n log n in the average or worst cases. All right. So what are we going to try to do now? Going to try to see, can we do better than that? Now, what do you mean we're going to do better than that? How are we going to do better than that? I just showed you, I just explained to you why it's got to be at least n log n. The answer is we're going to consider non-comparison based. In other words, what we just discussed with this decision tree model is if we're using comparisons. We're saying, how are we figuring things out? We're going to look at a pair of elements. We're going to compare them, see which is bigger, which is smaller, and make our decisions based on that. But we're going to look at other ways of sorting now. Okay, we call them the counting sort, radix sort, and bucket sort. Now, radix sort and bucket sort each use a counting sort as part of the sort. So counting sort is really important because it's the basis really for the other two. Okay, so how does counting sort work? So we basically keep track of how many of each number exist. Okay, that's why it's called counting sort. We're going to count how many 5s there are in the array and how many 7s there are in the array, how many 24s there are in the array, and so on and so forth, right? By the way, when is this counting sort useful? Okay, a counting sort is good if you tend to have repeats. So let's say you have a class. Okay, so in my CS 355 class, I have 75 students. Let's say I give an exam, right? So it's very likely that, you know, multiple students are going to have the same grade. Right, with 75 students, we expect many students to have the same grade. Even in our class, where we only have 46 students, there will be, you know, several people who get the same grade, right? So we could use a counting sort for that. Okay, it's not good if you know, expect everyone to have, you know, all the numbers are going to be different, particularly if you have, you know, decimal places, right? So then it becomes less likely they're going to have repeats. Okay, so here's what we do. We start by initializing our frequency array to 0. We're saying, so far we have 0 of everything. Then we count how many we had. So that's actually pretty easy to do. We'll show you how to do that in a second. And then we output a copy. So let's say we have 3 1s, right? So our array says we have 3 1s and 2 2s. So we write out 1 1 1. Then we write out 2 2. Then let's say we had 5 3s. We write 3 3 3 3 3. and so on and so forth. So we're now going to have a sorted array because the numbers are inherently sorted, and we just need to know how many of each thing do we have. So that's what this count does. Okay, this count is assuming it's counting characters. It says, okay, initially we're going to have nothing, right? We're counting the ordinal. Everyone know what OR does? OR tells you what character number it's saying. So as I find my characters, I'm saying increase the count of that character by 1. Okay, and what this does is it moves everything down, and then I write it out. All right, so this is a counting sort. So as with a lot of these algorithms, the best way to do it is with a picture, right? So take a look at this picture here. So saying, here's your data. Notice the data is not sorted, and the data is all in the range 0 to 4. So what we do is we count how many zeros we have. 1, 2, 3, 4, 5. So we say we have 5 zeros. How many ones do we have? 1, 2, 3. Say we have 3 ones. How many 2s do we have? 4. 1, 2, 3, 4. You get the idea. Okay, we don't have any 3s, so we put a 0 there. And now we have our sorted data. How did we do that? We said, okay, I have 5 zeros, write out 0 5 times. Right, that's what's happening over here, right? We're building the output array. Okay, I have 3 ones, write out 3 ones. I have 4 2s, write out 4 2s. I have no 3s, so don't write any 3s. I have 2 4s, write out 2 4s. So this is called the counting sort. Why is it called counting sort? Because that's what it does. It counts how many of each element you have, and then it outputs those back to some other kind of array. So how long does that take? Okay, so let's look at the code for that a second, right? How long does a for loop iterating over the elements in an array take?
O of n,
O of n, where n is what?
amount of elements in the array.
Number of elements in the array, correct. Okay, next we have another loop here. Okay, what is range of 256? The significance of the 256 is the number of different characters in the character set. So that's what we call O of m, where m is the range of the different possible characters. Then we have another loop. Okay, how long is this loop going to take? The third loop.
O of n.
O of n, correct? And finally, the last loop.
O of n.
Okay, good.
Okay.
Okay, so we have 2 kinds of loops. We have some loops that depend on the range of characters, and we have other loops that depend on the number of elements, okay? So if you look at those 2 together, we say, okay, well, it depends on m, n, and m. Now, which of these is bigger? We don't know. Generally speaking, the number of elements is bigger, and the number of different kinds of elements, right? The range, okay, going to be smaller, right? So the time is O of n plus m. If we assume that n is bigger, so it becomes O of n. All right, so this is a good. Why don't we just use this and be done with it? We'll skip merge sort, we'll skip quick sort, we'll skip BSD sort, we'll skip bubble sort, just skip all those other sorts. Why? This sounds great. O of n time.
Like if the data is big, you have to initialize it big.
Okay, so if you have, first of all, a lot of different possibilities, particularly if you allow decimal numbers, you can't start having an array cell for every different possible decimal number, right? So it's good where you have, let's say, integer numbers in a particular range. Now, if let's say you have 1 decimal place, can anyone suggest something can do like, you can't just say put it in position, you know, you're going to add 1 to position 6.5. So can anyone suggest like a little trick you could do to help us, let's say if we have 1 decimal place?
Like use fixed point.
You can't put, you know, you can't increase the count of 6.5 in an array, right? So
You-
what do you do?
Like if you know it's all 1 decimal place, you can't like.
So here's a trick you do. What you do is you take all your numbers and multiply them by 10. Okay, so now 6.5 will correspond with position 65. 7.2 will correspond with position 72. 3.8 will correspond with position 38. So now, even though your numbers have a decimal place, we can map them to integer positions in an array. So that's a little trick that we use. All right, now we move to radix sort. Right, radix sort. Radix is a fancy name for a digit. Okay, generally speaking, when we think of digits, we think of base 10, but you should know that many radix sorts do not use base 10. They'll use base 16. They'll use base 256. They'll use base 26 if we're dealing with characters, right? So it can be a lot of different kinds of bases. The example we're going to use in class today is base 10 because it's easy to think in base 10. But in reality, it often will use a different base. Okay, and look what it does. Okay, it's a very simple idea. We do one digit at a time, and we apply a counting sort to that digit. Okay, so that's what this is doing. It's basically doing one digit at a time, starting from the right and moving away to the left. That's why we're multiplying the exponent by 10, and we're saying do a counting sort on that digit. Okay. Once again, you're going to want to see the picture for this to really understand how it's working. I should clarify that there are two basic approaches to radix sort. One approach to radix sort is going from right to left, and the other approach to radix sort is going from left to right. The approach that we are doing today in class and that you'll do in assignment number 2 is going to be a right to left radix sort, but you should know that there are other kinds of radix sorts. So take a look at this picture here. Okay, can someone tell me what we are doing in the process of going from this first chart or array, whatever you want to call it, to the second one? So what's happening as we go from this picture to this picture?
I'm saying sort the last column.
We're sorting by the last column, or more specifically, the last digit, right? We're sorting by the last digit. Okay, then what do? Then we sort by the middle digits. Now, here's what is very important. Okay, when you sort by the middle digits, you have to be sure that within the sort, we don't mess up what we had already. Okay, so if we have a bunch of A's here, right, that are all going to get sorted together, we have to ensure that we retain the sorting of the B's before the D's. We can't mess up what we already did. So within the A category, we have to preserve the sort of all the A's. Within the B's, now there's only one there, we preserve the sort. Let's find another good example. We have 4 E's. We have to ensure that everything in the digits after remains in that sort order. That's called stable sort. We preserve the existing order, and that is key to a radix sort, because otherwise, if we sort one digit and mess up the other digit, it's no good. So we have to ensure that as we sort by a digit to the left, we preserve with relative to those any data, any sorting in whatever to its right. And that's what we do here. So can someone tell me, before we look at the next slide, what's the time complexity here? It actually has 2 pieces to it. So first of all, how long does it take to sort a column? 1 column. If we're using a counting sort to sort the column, right? If you look in this picture here, it's code using a counting sort. So how long does it take to? It's going to take O of n plus O of the time, you know, the number of different possibilities, but generally that's going to be small. Okay, so basically it's O of n. Now, but we need to do that sort multiple times, right? We need to do it for each column. So what else does it depend on?
How long the digits are?
How many columns we have, right? So in this case, we have 3 columns. More generally, we'll call that D for the number of digits. Okay, so here's our analysis, very simple analysis. We said O of n for the time for each column, multiply that by the number of digits, we get O times D of n. Now, the number of digits will generally be a constant, right? So then we can say, oh, then if the number of digits depends on n, right? The number of digits grows as the size of the data grows, then it becomes like n squared. But generally, that's not the case. Generally, if we're smart about it, the number of digits will be a fixed number. Okay, finally, we have bucket sort. Finally, we have bucket sort, okay? So what is a bucket sort? Anyone familiar with that? So by the way, that's how I sort stuff. Okay, so let's say I'm cleaning up my room. So I will, I have these big piles of paper. So I say, okay, anything related to my car is going to go into one pile. Anything related to my bank account goes into another pile. Anything related to my my job go into another pile. Anything related to my house goes into another pile, right? So you make these piles, and then you go back and you sort each of those piles in some kind of order. It could be chronological order, order of importance, but some kind of order. So the same thing in bucket sort. We take our data and we put it in buckets. Okay, so for example, let's say we're sorting social security numbers. So we'll take everything that begins the social security number 000 through 099 is going to go into one bucket. Anything that is in between 100 and 199 goes into a second bucket. Anything between 200 and 299 goes into a third bucket. So we put our data in the buckets. Now the buckets are not yet sorted yet. They're not yet sorted yet. Okay, so we need to do that. Once we have our buckets, we go back and we sort them. Now, how do we sort the buckets?
Use counting sort.
So actually, we don't use a counting sort because there could be too many different possibilities. So I might have confused you before where I said that these other ones.
Yes, sir.
So just one second. The counting part of it, the part that's like the counting sort, is actually what puts them in the buckets. Okay, because we're looking at the data to decide which bucket it goes into. But when we sort the actual buckets, we use a traditional sort. Someone had a question there?
I was going to say that we give a range to each bucket.
Correct. Each bucket is a range, right? So that's where the counting sort part of it comes in, is determining which bucket it goes into. But the sorting of each bucket uses another technique. Which technique? So generally speaking, insertion sort is good on the buckets if the buckets are small. Insertion sort works well on small amounts of data. So the idea is the way bucket sort works well is if you have a lot of buckets and each bucket is small. Why do you think that's true? Because if the buckets are big, then you haven't really done anything yet, right? You just have a huge sorting problem even within the bucket. So what you do is you have a lot of small buckets so that when we have to sort the individual buckets, they go quickly. And once you have, like, let's say 10 data elements or less, insertion sort is a good strategy. Okay, so here we have code for bucket sort. Okay, here is the code. Here we're just creating our buckets. Here we are deciding where to put it, right? Which bucket it goes into. And notice what we're doing. We're creating a list. We're appending the item to the list, right? Then we sort our individual buckets. Now, this particular bucket sort is using insertion sort to sort each bucket, and then we take the results. So we take all the things out of bucket one in sorted order, then all the things out of bucket two in sorted order, which, by the way, is a little bit similar to the counting sort. But again, we're not using counting sort to sort the individual buckets. Generally not. Generally, we use something like insertion sort or possibly another sort. Okay, so here we have a picture, right? We take our elements, put them in the buckets, we sort each bucket, and then we output the contents of each bucket. So this one has a 3 and 9, this one has nothing. This one has 21, 25, 29, this one has 37, this one has 43, 49, and we output that, right? So that's the basic strategy of bucket sort. And there are really 3 pieces to the bucket sort. So we got to put everything into the buckets. we need to sort each bucket, and then we need to concatenate. So the good news is this last piece of concatenating them, writing it out is fast. That's linear time. And putting them into the buckets is also good because we just use like a hash function to put it in. The question is, what about sorting all the buckets? So which sort did I say we often use to sort the buckets?
Insertion sort.
I said you recommended that you use insertion sort. So let's do the math for that. Who remembers what is the time for insertion sort? So if you have n elements, in the worst case, okay, generally we use the worst case. What's the time for insertion sort?
O of n squared.
O of n squared, correct. All right, so in this case though, do we have n elements in each bucket? We started with n elements, okay? How many elements should be in each bucket? Let me ask the question again, right? If I have B buckets and I have a total of n elements, so what would we expect to be in each bucket?
N over B.
Average.
Say it again.
N over B.
N over B, right? So that's what this is saying here. It's saying in the average case of insertion sort, right? We said it's like n squared over 4. So we're saying each bucket has like n over B because, only, not all of them are in one, right? So it's going to be n over B squared over 4, which is n squared over 4B. Now, is this proportional to n squared or is that like n, this thing here? So let's say B is 10. So now if n squared over 40, is n squared over 40 considered n squared or is that considered n?
N squared.
That's considered n squared. So how did that help me, right? How did that help me if the total work is n squared over 4b, if b is a constant, so now I just have n squared again. So I did a lot of work for nothing. So here's the answer. If the number of buckets depends on n, right? Let's say it's n divided by k. So if I divide that by n over k, I get O of n of k, which is order of n. So here's the rule. Here's the rule. If the number of buckets is dependent on n, then it's going to be linear. If the number of buckets is not dependent on n, then it will be n squared, quadratic. Okay, so here's the strategy. When you do bucket sort, make sure that you have a number of buckets that compared to, proportional to the number of numbers. Okay, you can't just say I'm gonna use 4 buckets and I have, 10,000 elements. If you have 10,000 elements, use 1,000 buckets. If you have 1,000,000 elements, use, 100,000 buckets, or at least 10,000 buckets, right? You want to make it proportional to that. Otherwise, it's going to be an n squared algorithm. Now, this is an average case. What happens in the worst case? Look back over here. What does it say? Look at the first bullet. Right? It is possible that all the elements fall in one bucket. Let's say I gave an exam and it was a really easy exam. So everyone got 99 or 100, right? So everything's in one bucket. Or let's say it was a really hard exam. Everyone gets, I don't know, between 10 and 20, did really poorly on the exam, right? So it is possible. Or let's say you put people in buckets by height, and it happens to be a convention of the tallest people in the world convention, right? So everyone's going to land up in the same bucket because they're all, 7 feet tall. Understand? So depending on the data, it is possible that all the elements or most of the elements are going to fall in one bucket, in which case a bucket sort doesn't really do you any good. So bucket sort works nicely in the average case when you have a good number of buckets. If you're cheap on the buckets, you wasted your time. So we have a nice summary here. Okay, here we have a summary of both time complexity and space complexity. All right, we didn't spend too much time on space complexity, but we did spend some time on the time complexity. But let's take a look at the space complexity column anyway. Okay, so most of them are O of one. O of one means you know you have individual variables, primitive data types, but nothing that dependent on that. Can you tell me what are the exceptions, and let's try to understand the exceptions. Okay, so which ones are not O of one, and let's try to understand why. Okay, it shouldn't be that hard to see which one is not O of one. So I really would appreciate if someone could answer that for us.
They are quick sort, merge sort,
Okay, so one at a
line
time.
sort.
Quick sort, okay? So why is quick sort O of n? I'm sorry, O of log of n. We didn't really say that before, so it's not, I wouldn't say it's obvious. So does anyone have a suggestion why it's log of n and not O of one, right? We didn't see any extra array. It's not like merge sort, right? So the next one is merge sort. We understand that hopefully at this point, right? Because when you merge the items, you need to merge them into another array. Anyone have any suggestions? Okay, so it's implemented recursively. So when you first learn about recursion, or maybe not when you first learn about it, but how does the computer, the language, remember what you're up to? Anyone know what we call that?
Stack frame.
A stack, right? I mean, it's sort of like a stack data structure, but it's not a stack in that, right? It's got to remember, right, where you were up to. So that takes space. That takes space. Okay, how much space does it take up? Well, it takes up depending on how many layers of the recursion there is. All right, so that's where that log of n coming from. Okay, so again, if you looked at the program, you would not understand where that log of n is coming from because you wouldn't see an array of size log of n. That's really for the stack because it's recursive. So it has to keep track of what it's up to. All right, so that's where that log of n is coming from. Okay, the merge sort, we said it needs an auxiliary array to copy it into. So potentially, you know, in the last phase, it's got to merge n elements in. So you understand why it's O of n. Tim sort, which is like a combination of merge sort and insertion sort. All right, basically it looks for streaks, right? It looks for, you know, a sequence of elements that are in a row. So since it's merge sort like, that's where the O of n comes from. All right, let's go down to a bucket sort. Can someone tell me why bucket sort is not just plain O of one?
Because you're creating buckets to store the data.
That's correct. Okay, you're creating buckets in which to store the data. Okay, so those buckets, you need one slot for each item. There are n items. Good. Okay, what about radix sort? So remember, radix sort uses a counting sort. So counting sort depends on the amount of data and depends on the range of data. So the K represents the range. And we called it M before. This slide, which I took from somewhere, calls it K. That's basically what it is. K represents the range and N is the number of elements. So counting sort needs that space. That's one of the drawbacks. Counting sort requires a lot of space. Okay, counting sort, you know, depends on the K. And finally, we have cube sort. We did not discuss cube sort. You're not responsible for cube sort. Okay, so.
Professor, I have a question.
Yeah.
Why is heap sort has a space
Oh.
complexity of O of 1.
Okay, good question. Anyone want to answer that question? So remember this, every algorithm requires n space, right? We have n elements, it's n space. So why are all those green ones there with the O of 1? The answer is we only count the space that is extra beyond the data, beyond the original data. So bubble sort, insertion sort, selection sort, shell sort, don't use any extra space. Okay, so you're asking what about heap sort? So you could build a heap separately using a tree structure. As one of the students mentioned at the beginning of today's class, right? It's usually done in place. It's done inside the array itself. Okay, let's just do, are there any more slides or is this the last? So this is just another summary. Okay, so I just want to show you, we go back to the heap sort, right? There's nothing here about building an auxiliary storage, right? You could build it with a tree, a binary tree, and have a left pointer and right pointer, but we don't, that's not how it's usually implemented. It's you implement it in place, in the array itself, right? So even though it looks like a tree, but it's a tree that is driven by, it's like a mapping, it's almost like a wrapper of the underlying array. Did that answer your question?
Yes, Professor, thank you.
Okay, good. All right, so we're actually doing well on time today. So what I'm going to do is I'm going to do some of the material that's related to today's lecture, but normally I don't get to it because normally my lectures are an hour and a quarter, and in the summer they are longer. So what we're going to do now is we're going to do some material related to today's lecture that I would normally do as part of trees, and then we'll have more time to discuss trees. Okay. So in order to do that, I'm going to import them into here. So watch this, we're going to do a little trick here. Okay, I'm going to put it, actually where it belongs, okay? I'm going to put it right before them. Okay, so I know we're going to make it a little bit out of order compared to the lecture, but decision tree, heap sort, I do it right over here. Okay, so here's what we're going to do. We're going to import them from the other one, import slides, and get it like this. Okay, and let's find, we did the binary search tree, traversals. Okay, binary, quick sort, average case, and that's what we need. Okay, good. Okay. Okay. All right, so let's, we're going to back off a step here. And right here is, remember, our binary search tree. And we said we can sort with a binary search tree, right? By building the binary search tree, we do an in-order traversal. And then we have the binary search tree. All right. Okay. Okay, so we said that there's a connection between binary search tree and quicksort, right? The root is like a pivot. We break it up into the left and to the right, and then we do an order traversal. So what I'd like to do with you now for the remainder of the class, maybe it'll be the remainder of the class, is to do the average case analysis of quicksort, okay? So if you go back to quicksort, yeah, I'm just going to create another slide here. Okay. Okay, so let's do this. Okay. Okay, so this is a slide which I took from a book. Okay, they're using C. Why are they using C? So we normally use T for time. Why are they using C? Anyone want to guess what C stands for? Cost. Okay, so we're going to say as follows. The cost for N is equal to, okay, I'm going to say this. Cost for 0 plus the cost for n minus 1 plus n minus 1. Okay, what does this represent? Okay, so I'm going to put a little comment here. Okay, where is the pivot in this case? If all the work is on one side. Everyone see that all the work is on one side. Where's the pivot?
In the middle,
No, in this case, if it's all on one side, the pivot is in first position. Okay, then we have. Okay. Okay, so I'm going to say plus C of 1 plus C of n minus 2 plus n minus 1. So there's always n minus 1 work in each level. The pivot is in the second position. Okay, plus there's a possibility. Oh, you know what it's doing? It's making the plus into a at. Okay, plus there's a possibility that the pivot is in the next position, right?
Kind of confused, Professor. So which one's the pivot? It's C0 and C1 and C2.
Well, no, what this is saying is it's the work on the left side and the work on the right side, plus the work to break it up. Okay, let's go back to what quicksort looks like. And by the way, the same is true for the right. So let's say the pivot is here, right? So now I have 4 elements on the left. So I now need to process the 4 elements on the left, and I need to process the 4 elements on the right. Okay, so at each stage, right, depending on where the pivot is, I'm going to have to do some work on the left and some work on the right. But where is that pivot? Well, it could be in a lot of places, right? It could be in the first position, it could be in the second position, it could be in the third position. So depending on where it is, right? So I'm going to say ... here. And now let's do one more for the last position. So if it's in the last position, what does it look like? You got all the work is on the other side, on the left-hand side now, right? And there's nothing left to do on the right-hand side if it is in the last position. Okay, now we want to take an average. So what do we need to do? This is all the different cases.
Add them all up and divide by the amount.
That's correct. So they're already being added up because you see the plus sign. So now we take the average. Take the average by dividing by n. Okay, so this is an introduction to the next slide. It says to get the average, you have to figure out all the different possible positions of the pivot, right? If the pivot is in the first position, I have like no work to do on the left. All the work is on the right. If it's in the first position, then I've got one thing to worry about on the left position and n minus 2 on the right. So that's what this is saying here. Okay, so take a look at this picture here. It's saying, okay, and by the way, they're using n plus 1. So just to be consistent with that next slide, I'm going to write it like this. Okay, that depends on exactly how you code the partition algorithm. but just so it leads more naturally into the next slide, I'm going to do it their way. So depending on how you code it, it could be n minus 1, n plus 1. I want the slides to be a little bit consistent. Okay, so what this is saying is as follows. There's n plus 1 work to break it up into the two parts. Now we need to take the average. Okay, need to take the average. So we're saying, right, I have C of 0 plus n minus 1, right? The next case in the sum is C of 2 minus 1, which is C of 1, and n minus 2, and so on and so forth. And I need to take the average of that. So that's what's happening in this first line. Okay, anyone have any questions they want to ask about that first line? So again, we're taking an average of all possible cases. By the way, I don't need this. I don't think I need part 1 because I could, yeah, part 1, fine. Okay, so we're averaging over all possible cases. Now, who can tell me what's happening as we go from this line to this next line? It looks like we're combining something. What are we combining? So look at what has changed. What has changed from the first line of this analysis to the second line? So you don't even have to understand it to be able to say what has changed, right?
Is n minus k.
Okay, so what happened is it looks like the n minus k disappeared. Now, you can't just cross something out. So did we do something to, sort of counterbalance that?
So it seems like it's treating k minus 1 and no, ck minus 1, cn minus k the same, so it multiplied by 2.
Correct, correct. Now, the question is, why is that true? All right, so we need to go back to something from Gauss. All right, here, I'm going to create another temporary slide here. All right, so let's do this. We're going to make another new slide. So watch this. Okay. All right, so we have a sum, right? We had, what did we have in 1, right? The way they wrote it's k minus 1 and c of n minus k, right? Yeah, is that what they did? Okay, so what are the first terms? Let's say as k goes from 1 to n, right? That's what's going to happen on the next page. Yes? You agree with that? Okay, so let's look at the first term. What is that first term? It's c of 0 plus c of 1 plus c of 2 plus ... What's the last term going to be? The last version of that first term. So when I plug in n, what do I get? Plug in n for k, and what do I get?
N minus 1.
Correct, c of n minus 1. Okay, let's look at the second term. Okay, so what do I have? I have, what's the first instance of the second term? I have n minus k is 1. What's the next one?
N minus 2.
Correct. And the next one is n minus 3, and so on and so forth. And what's the last one going to be? So plug in n for k.
0.
Correct. Add these two together. And what do we get? We get 2 times c of 0 plus 2 times c of 1 plus 2 times c of 2 plus dot, 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 2 times c of n minus 1. Everyone see that? So one is going up and one is going down. Okay, which is equal to, so we could say pull, better yet, fancy word is factor out the 2, and we get 2 times c of 0 plus c of 1 plus dot, 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 plus c of n minus 1. Okay, let's put some bullets there if you like.
Professor, is the second term supposed to be the last term? No.
Well, it's the second of these two terms. So maybe I should be more clear. In pair above and second term. Is that more clear? Yeah.
Yeah.
Okay. So that's what's happening over here. Okay, we need a little of a commentary, right? We're saying, hey, these two sums, if you think about them, they're the same thing, just in opposite orders. Yeah. Okay, what are we doing next? Okay, so this also isn't really so obvious. So we're going to do a little trick here. Okay, so we're going to do another intermediate slide here to explain what's going on. So new slide. Okay, call it average case analysis. Okay, and so what did we get to at this point? We had C of n equals n plus 1 equals n plus 1 plus 2 over n, and then we had a summation. Let's see if we can get a simple special characters. Where did it go? All right, it's not going in that way. Okay. Oh, it did show up there. Okay. So we have 2 times n times the sum of what goes in there. Right? We said C of, I don't remember, we'll look. C of k minus 1. Okay, so what we're doing now is we're doing a little trick here. Okay, we're going to multiply each side by multiply each side by n. Someone tell me why we're doing that. Why would we want to multiply each side by n? What's that going to do for us?
To get rid of 2 by n.
That is correct. Very good. By the way, who's talking? Is that Ilma?
Yes.
Okay, thank you, Ilma. Good observation there. Okay, so we're going to put an n there. We're going to put an n there. And we're going to multiply by n, which means we get rid of the n on the bottom, right? So that's nice. Okay, now create another instance for n minus 1. Okay, what do I mean by that? We're going to plug in, let me say it differently. Log in n minus 1 for n. Okay. Watch this. How are we doing on time? Still some time left? Okay, so we're gonna plug in n minus 1. Okay, so wherever you see an n, we put in n minus 1 with n minus 1 plus 1 there. And here we have n minus 1 there. And over here, we have an n minus 1. Everyone see what I did? I just took my original equation and I put in n minus 1 across the board. Okay, and now we're going to multiply each side by, what do you think we're going to multiply each side by? So think about what Omar said before. What were we trying to do before? Trying to get rid of the n that was on the bottom. So now we have an n minus 1 on the bottom. What do you think we should multiply by?
n minus 1.
N minus 1. Good. Okay, so we're going to multiply by n minus 1 over here. We already had n minus 1 over there. N minus 1, I'm sorry, multiplied by n minus 1 there. And that n minus 1 is going to go away. Okay, good. Now, watch what we do. We subtract. Going to subtract n times c. Okay, so we say first. So we have n c n minus n minus 1 times c n minus 1. Okay, and what's that equal to? So this is our left-hand side. Okay, we're going to do right-hand side is what? So let's grab it. Okay, so here's our right-hand side. And subtract all that. From the second one, right? So this was the second one here. Okay, so we're going to simplify the right-hand side. Okay, what do we get? Can anyone? And let's just be more clear here. This was as k equals 1 through n. And this one here was as k equals 1. Okay, so what happens when I subtract n times n plus 1 and subtract from that n minus 1? Something's wrong here. I multiplied each side by n minus 1. Oh, I should have n minus 1. This should be n. This should be n, right? Because I plugged in n minus 1 plus 1 is n. And that means here I should have n minus 1 because I took the n and I multiplied by n minus 1. So therefore here I have this. Okay, so if I take n times n plus 1 and subtract n minus 1 from that, what do I get? Could write it like this if you like. N plus 1 minus n minus 1 times n. And what happens when I subtract this sum here from that sum. So I have this sum here, and I have this sum here. They look like the same, except what? What's the difference between those two sums?
One goes to n-1.
One goes one term more, okay? So I just need to add that last term. So I get 2 times C of the last term, which is the C of n. Right, because all the other terms fall out. I'm sorry, it's going to be C, it's K minus 1 where K is n. So it's going to be this. Okay, can we simplify that a little bit more? What happens to this? We should be able to simplify that a little bit. So I have an n squared and I have an n squared. They cancel. I have an n and I have a minus minus n is 2n. So I have an n and an n makes 2n plus 2c of n minus 1. So what do I get? What happened on my left-hand side? I had n, c, n plus minus n minus 1 c of n minus 1 is equal to 2n plus 2 c of n minus 1. Okay, what do you think we could do to this? We have n minus 1s and c of n minus 1s on both sides. So what do we get? N c n equals 2n. And if I put my cn minus 1s together, actually I could do it this way. How many c of n minus 1s do I have? I have n minus 1 here. I add them to this side. So now I have n plus 1. N minus 1. Okay, you see what I did? I moved cn minus 1 from left side to right. Okay. Now I'm going to divide by n times n plus 1. Okay, so what do I have? I have n c n divided by, I need a colon there. Divided by n times n plus 1 plus n plus 1 c of n minus 1 divided by n times n plus 1. Okay. Just make this a little smaller. More. Okay. Can anyone simplify either the left or right side?
Well, you can get the over n times n plus 1 because on both sides, right?
Say it again.
Never mind. I'm sorry, I made a mistake.
Okay, so look at the left-hand side. Can you simplify that for me?
Yeah, you can take out the n from both the top and
You
bottom.
can take out, I have an X, okay, so we're gonna simplify that. So we get C of n divided by n plus 1. What about on the right-hand side? Can we simplify this?
Yeah, the first time you can take out the n, and the second one you can take out the n plus one.
Second, okay, we take out the n. So we get 2 over n plus 1. And on the second one, we take out the n plus 1. So we get C of n minus 1 divided by n. Okay, so let's gonna duplicate that slide. And let's start from that point onward. Okay, so we're going to do a little trick here. Okay, here's the trick. We're going to do something called a range transformation. And a range transformation, you change the function from, you can divide by something or multiply by something. So we're going to say, let d of n equal C of n divided by n plus 1. Okay, we call it range transformation because we're changing the range. It's still a function of n, but we're changing the nature of the output. So what happens to our substitute d of n into above? Okay, so what happens to the left-hand side? What does this become?
D of n.
Correct. D of n. Good. And what does this thing become? It stays as is. Okay, so we have 2 divided by n plus 1. And what does this next thing become? If d of n equals C of n over n plus 1, what does that look like to you? That's the same as d of n minus 1. Okay, now we're going to move d of n minus 1 to right-hand side. So we get d of n minus d of n minus 1 is equal to 2 divided by, I know there's a lot of stuff going on here. And then we're going to substitute n minus 1 for n. So what do we get now? Copy that. We say that's d of n minus 1. Okay, now we're going to do substitute n minus 2. Okay, sort of like what we did back with the original recurrence. Okay. Okay, so we just repeat this process until we get down to 0. We get n minus 3 minus d of n minus 4 equals n minus 3. This becomes n minus 2, etc. And the last equation will be d of 1 minus d of 0 is equal to, you plug in, so you get 2 of, plug in 1. We're going to get 1 plus 1, which is equal to 2. Okay. Add all these up. What happens when I add up all these equations? Remember telescoping? What was the concept of telescoping? When I have a whole bunch of equations, remember the telescope? What happens when I collapse the telescope? Everything comes together, right? When I Okay, so all these terms are going to cancel, right? The dn minus 1 is going to cancel with this dn minus 1. The minus dn minus 2 is going to cancel with this. So what do I get? dn from the first one minus d of 0 from the last one. And I have the sum of 2 over n plus 2 over n minus 1. N minus 1. Plus 2 of n minus 2, etc. And my last term is going to be just plain 2. Okay. What is d of 0? d of 0 is equal to c of 0 divided by 0 plus 1. Okay, how much work is there in C of 0? How much work does quicksort do when there's no elements?
Constant time.
No work. Okay. So it does no work. Okay, which is just 0. Let's just. Okay. So we have d of n, and what's this equal to? Anyone know what that is? Does that remind you of a series from calculus?
Geometric series.
No, you're on the right track though. The harmonic series, right? Multiplied by 2. Okay, because it's right, it's 1 plus 2 plus 1 over 2, 1 over 3, 1 over 4 up to 1 over n, which is equal to ln of n, or I should say approximated by. All right, so what we are left with, and we're almost done. Okay, so we have d of n is, I'm going to say equals, but it's really approximately Okay, so d of n is approximately, maybe I should say it like that, approximately equals to ln of n. And one last line here, what is c of n? C of n is equal to n plus 1 times d of n, which means that it's approximately equal to n plus 1 times log of, which is approximately equal to 1.4 n plus 1 of LG base 2 of it. Okay. All right, so if you're ever wondering why it is n log n, that's where it comes from. Okay, so I know there's a lot of math there. a lot of different techniques that we're using, but that's where it comes from. So good news is you're not going to have to solve this equation on the exam, but you should have some idea where this n log n came from. It wasn't just made up. All right. So that's the idea, and we're going to stop there. Okay. If anyone has any questions, so that's the end of lecture. If anyone has any questions about assignment number 2, so assignment number 2 is very similar to assignment number 1. Assignment number 1 we did together. Assignment number 2 is basically taking sorting algorithms from the internet and plugging them into our framework, our template that we created in assignment number 1, and getting some analysis. You might find that, you know, for big N, the algorithms are too slow. And if that's the case, just, you know, change, you know, don't go up to 10,000. You can use your highest N to be 1,000, and that's okay. You can prove the same idea. All right, so that is it. Just remember to do the top hat code for today. I'm gonna make sure you do the top hat code. Someone wanna?
Yeah, do we have like a good solution for the time being 0 on some of our computers?
What, for the sorts?
Yeah, sometimes it doesn't like recognize a time greater than 0 for like a lot of the sorts. What I did last time was
Well, so you have to figure out what the issue is. Is it really going that fast? Or is there something else going on? So, I mean, use sizes of 10,000 and see if it's finishing or not.
I tried 10,000. It didn't finish overnight, so I kind of gave up.
Right. So then then it's not really 0. So what's going on? There's something else. You gotta debug. So where is, you know, print the time before and after. Do you see a change, right? Pick a large N. There should be some kind of time.
Okay.
You understand what I'm saying?
Yeah.
So either it's really fast, but then if you do, you know, 10,000, then it should still be really fast. So if it's not so fast, it means your program is probably doing the sorting correctly. You just have to figure out what the time is. So, you know, print out the start time before, print the time after. Do they look different? Does the time change between them?
Okay, I guess I could try to see.
Yeah. I mean, if you want, we could look at it now. I have 15 minutes before my next class, or you could, you know, debug it on your own. But if it's taking, when you know, make the N bigger, if it's taking longer, then that probably means that's a good sign, right? So now the question is, why is your timing not working? So if you print out your start time before, print out your end time afterwards, see, do they look different? If they don't look different, then there's something wrong with that time function. There are also other ways, you know, to get times from the operating system. You could, you know, look around for those, but just check if the time variable, the start time and the end time are exactly the same for a large N. Probably they should not be.
Okay, I see. Yeah, I'll try it out. Thanks, Professor.
Okay.